The Voyager 2 spacecraft has finally bid farewell to our solar system, decades after it was launched in the 1970s to explore the gas giants and the outer reaches of our celestial neighborhood. Recently, it made a discovery that sent shockwaves through the scientific community and beyond. Initially, the signals it transmitted appeared to be mere blips, indistinct data that resembled background noise typical of interstellar space. But soon, patterns began to emerge, high-energy particle readings of such anomalous intensity and rhythm that even seasoned scientists were left unsettled. These bursts of radiation, growing stronger with each transmission window, carried within them a structure, oscillations interwoven with chaotic spikes, that suggested something deliberate, possibly intelligent. At first dismissed as a malfunction, these signals were meticulously analyzed, with every technical anomaly ruled out. Still, the readings persisted. What Voyager 2 detected appeared to originate both impossibly far away and disturbingly close, as if some unknown force in the universe had awakened. As the reality of the discovery sank in, discussions spread beyond engineering teams to astrophysicists and planetary scientists. The intensity of the particles surpassed anything previously recorded near Neptune or at the heliopause. Their spectral distribution hinted at violent processes beyond solar flares or even supernova remnants. The data suggested the existence of a powerful, unknown cosmic engine, one capable of accelerating particles across light years. This set off a global scientific and observational effort. Ground-based observatories and space telescopes alike were redirected to monitor the region. And then came the most chilling revelation. The modulation of the particle bursts bore signs of structure, possibly even intention. Was this a natural phenomenon that mimicked intelligence? Or was it a signal? The idea that Voyager may have stumbled upon a cosmic beacon, broadcasting with malevolent purpose, captured imaginations and ignited both fascination and fear. On Earth, theories proliferated. Some believed Voyager 2 had encountered a dormant interstellar relic, possibly a remnant of an ancient civilization. Others feared a catastrophic stellar collapse was underway, one capable of unleashing radiation waves strong enough to eventually threaten Earth. Would our planet's magnetic field hold? Could our technological infrastructure endure? The implications were not just theoretical, they were existential. Scientific councils convened, mission priorities shifted, and data analysis became the world's top priority. The spacecraft, drifting more than 18 billion kilometers from Earth, had become a sentinel on the front lines of a vast unknown. Why now, after years of silence in interstellar space, had this phenomenon emerged? Was it a shockwave from a long-ago supernova? A denser region of exotic plasma? Or something more dynamic and unexpected? Despite the magnitude of the event, no other observatories on Earth or in orbit detected anything comparable. Voyager 2 was uniquely positioned for this encounter, and its recordings remained unmatched. The mystery captured public attention worldwide. Media outlets speculated about alien contact, secret government knowledge, and apocalyptic timelines. But amid the noise, scientists focused on decoding the signal. Mathematicians, linguists, and cryptographers approached the data as if it were a Rosetta Stone from the stars. Algorithms scoured for patterns, and neural networks searched for hidden messages. Yet every new insight only raised more questions. Was this a stable structure or an evolving one? Did it contain a syntax, a grammar? Or was it a chaotic but natural cosmic artifact? What became clear was that, regardless of its origin, the phenomenon posed real risks. Earth's power grids, satellites, and communication networks could all be affected by surges of high-energy particles. As a precaution, agencies began to draft shielding strategies, increase fault tolerances, and design early warning systems based on Voyager 2's data. Across the globe, an unprecedented spirit of scientific collaboration emerged. Space agencies, universities, and private industry pooled resources. New disciplines formed: interstellar meteorology, planetary defense planning, and magnetohydrodynamic forecasting, blending astrophysics with engineering and policy. Cultural responses mirrored the scientific urgency. Museums curated exhibits, composers turned data into music, artists visualized plasma bursts, and students built their own detectors. Educational programs incorporated Voyager 2's findings, and global classrooms became part of a shared mission to understand the cosmos. Meanwhile, politicians debated how to fund both earthbound crises and cosmic preparedness. Defense committees drafted protocols for galactic-scale events, and companies developed radiation-hardened technologies for space travel and terrestrial protection. Biotechnology firms explored radiation-resistant materials, while new generations of deep space probes were planned, each one a sentinel in a growing planetary shield. Still, Voyager 2 remained the heart of the mystery. Its fading instruments, powered by dwindling plutonium reserves, continued to relay data that stretched the limits of physics and imagination. Statistical patterns in the data suggested periodicity, prime number sequences, and fractal structures, clues that hinted at either a profound natural process or something crafted. The galactic dynamo hypothesis gained traction, proposing that relic magnetized turbulence from ancient supernovae might be fueling these cyclical surges. If true, the data could one day allow us to forecast cosmic radiation storms months in advance, just as we now predict hurricanes or solar flares. This discovery reshaped our view of interstellar space. Once thought to be tranquil, it now appeared dynamic, volatile, even dangerous. Yet with that realization came a wave of innovation, unity, and introspection. From urban power grids to rural observatories, from deep space labs to art galleries, humanity responded not with fear alone, but with collaboration and curiosity. The anomaly spurred changes in space exploration plans, new funding for radiation-resistant habitats, and the idea that the next generation of spacecraft must not only explore, but also guard against the unpredictable forces of the cosmos. Ultimately, Voyager 2's legacy shifted from one of exploration to one of warning and inspiration. Its golden record, once a message of peace, now accompanied signals of immense cosmic energy, a stark reminder that the universe is not silent. And yet, amid the storm, a flame of human resolve burned brighter. We had glimpsed the unknown and chosen to face it. Voyager 2's final years, though silent and distant, would echo across generations, reminding us that even in the vast emptiness of interstellar space, one fragile probe, and the species that built it, can still make a difference.